The single biggest issue facing humanity is climate change. A warming of 6 degrees will mean the complete collapse of our weather systems. In the scale of a single lifetime, the availability of freshwater resources will ensue a human migration on the order of billions. Without action, the Cambridge Centre for the Public Understanding of Risk calculates there's a greater than 1 in 2 chance of either annihilation of intelligent life on Earth or the permanently curtailing our potential development. We must consider our energy sources, and the solution is solar energy. More solar energy falls in 20 square kilometres than is required for the electrical needs of all UK homes in a single year. But for the solution to be widely accepted, it must be cheaper than the current alternatives, and that is where my PhD comes in. We capture solar energy using sand. The second most abundant element on Earth can be made into a good and relatively cheap solar panel. Yet they remain inefficient. I'll explain why. Every material has a series of energy levels where electrons live. Each level corresponds to increasing energy, and two electrons can live on each level. Think of it as a ladder. Now, in a solar cell material, a photon comes in. It gives energy to an electron and excites it over this gap to a higher energy level. The electron then drops down to the top of the gap, releasing that energy as heat. Then the electron drops down again, but here we can capture this energy as electricity. But this means we're wasting a lot of the energy as heat. And this is why solar cells are so inefficient. At Cambridge, we have come up with a process to make this much, much more efficient. But to do so, we must split the electron. We call it singlet fission. We do it in a molecule which looks like this. This molecule accepts a photon like before, exciting an electron like before. But now, this is the cool part. It splits it into 2, which are half the energy. These electrons are now turned back into photons, which perfectly match the gap. This means that our solar cell can absorb these photons without wasting energy as heat, because they perfectly match the gap. This makes our solar cells doubly efficient. But that's all the theory. I can go one step further. For the first time, I have integrated that molecule into this bit of plastic. Not only can you see it as red light, which is perfect for silicon, but you can see it as brighter on the edges than the light coming in. We have developed a method where I can get 2 photons from one, and I can concentrate the light. This means I can develop solar cells which are cheaper than coal or gas or nuclear, and in the process, saving the world. Thank you.
Thank you, Tomi. Thank you.